friends. My oldest son had an imaginary friend. I don't know if you did, but we are going to look at some imaginary friends. So Pi says, get real, and the I says to Pi, be rational. I have a t-shirt. I should have worn that today. Maybe I'll wear it tomorrow. All right, Mrs. McInerney loved numbers when she was growing up, so much so that she even had a friend that was a number. That friend, of course, was imaginary. What was so special about that imaginary number? How can there be a number that isn't real? So, what I want to do to lay a foundation for this is I want you to try 1 and 2 on your own. These are things you know. These are things you already know. So, let's start here. And if you do have any club photos, feel free just when it's time to get up and go. So for 1A, you're just collecting like terms. For 1B, you've got to be careful to distribute the minus sign, so you get negative 6x minus 3. Letter C, you're going to FOIL this. This is 15 minus 12x plus 5x minus 4x squared. So let's check these 3. Did we get those okay? Thumbs up? All right, now, in number 2, we have done this, and you did it in Algebra 1. In 2A, if you want to solve x squared equals 9, what do you need to do? Yeah, Nick?
Square root of x squared.
Yep. And you're going to get plus or minus the square root. So you get x equals plus or minus 3. In letter B, we're going to first add 4 to both sides. Divide by 3. And I get x equals plus or minus 3. Letter C, I'm going to subtract 2 from both sides. Now, we typically don't like to say divide by 1/3. It's tough to divide by fractions. So there's another way. There's another. What could I do instead of dividing by 1/3? Multiply by 3. So let's multiply by 3, and I get x squared is 9. So I get x is plus or minus 3. All right. In letter D, can you think of a real number that when I take it times itself, it's going to give me negative 9? No, 3 times 3 is 9. Negative 3 times negative 3 is positive 9. This is not a real number. Today we're going to be able to answer this question. So throughout the development of mathematics, new sets of numbers have been defined in order to solve problems. Mathematicians have defined fractions and not just whole numbers, negative numbers and not just positive numbers, irrational numbers and not just rational numbers. For the same reasons, we also have square roots of negative numbers, not just square roots of positive numbers. Numbers that include the real numbers as well as the square roots of negative numbers are called complex numbers. So let's make a little history connection. Since the 1500s, okay, so that's a really long time ago, the square root of a negative number has been called an imaginary number. In the late 1700s, the Swiss mathematician Leonhard Euler, and it is pronounced Euler, introduced the symbol I to represent the square root of -1. He wrote, "It is evident that we cannot rank the square root of a negative number amongst possible numbers, and we must therefore say that it is an impossible quantity. But notwithstanding this, these numbers present themselves to the mind. They exist in our imagination, and we still have a sufficient idea of them, since we know that by the square root of -4 is meant a number which, multiplied by itself, produces -4. For this reason also, nothing prevents us from making use of these imaginary numbers and employing them in calculation. Defining imaginary numbers made it possible to solve previously unsolvable problems." So why do we have imaginary numbers? The imaginary unit I allows us to find solutions to many equations that do not have real number solutions. Complex numbers occur in the study of quantum physics, as well as in alternating currents and fluid dynamics. In the real world, they give insight into how to pump oil in oil rigs, how earthquakes shake buildings, and how electronic devices such as transistors and microchips work on a quantum level. You benefit from imaginary numbers, electricity, when you are charging things or using heat in your home or turning the lights on. Your washer dryer, your cell phone, your iPad. So it really, really is truly useful, and we should be very, very thankful for the people over hundreds of years who worked on this. So here's the deal. The imaginary number I equals the square root of -1. And I squared, when you take I times I, it produces -1. So from this moment forward, we're going to be able to handle a square root of a negative, and it's called a complex number. All right, so if I have I to the 0 power, well, we learned anything to the 0 power is 1. I to the first is I squared is -1. So again, these are my two new things. And then everything else is going to flow from those two. So if I have I cubed is going to be I squared times I. But what is I squared? -1, okay? This is what's new. I squared is -1. So I cubed is -I. I to the fourth is I squared times I squared. So William, what's I squared? -1. So if I take -1 times -1, I get 1. So I to the fifth, so here's something kind of nice. I to the fourth is 1. We just figured it out. I to the fourth is 1. So I can rewrite I to the fifth using my exponent properties as I to the fourth times I. So then what is I to the fifth? Nope, it's not I to the negative 1. It's not negative 1. It's I, right? Because what's I to the fourth? 1. 1 times I is I. All right, so I to the sixth, I can make I to the fourth times I squared. All right, so Hannah, what's I squared? Negative 1. So I get 1 times negative 1. So I to the sixth is negative 1. Okay, I to the seventh is I to the fourth times I cubed. So Avery, looking back at letter E, what's I to the fourth? 1. And then looking right above it, DP, what's I cubed? Negative I. Then I to the eighth is I to the fourth times I to the fourth. So that's 1. Now I want you to pause a moment, and I want you to look at this first group that I have. Is there a pattern? Yeah, Brendan?
All of the numbered exponents equal 1 or negative 1.
Say that again.
All of the even numbered powers equal 1 or negative 1.
Good job. Okay, so any of the even powers are 1 or negative 1. What else do you notice?
The odd exponents equal I or negative I.
Good. The odd exponents are I or negative I. Now I'm hoping for a more global. Those are true. Those are true patterns. What else is there? You got an idea, Mia?
It was
And then it repeats, right? Okay, so here's the big idea. It goes 1, I, negative 1, negative I, and it repeats. 1, I, negative 1, negative I. 1, what's this one? I, what's this one? Negative 1, negative I. Okay, so every 4, it's going to repeat. Okay, every 4, it's going to repeat. So this one is I, negative 1, negative I. So is there a pattern? Yes. Every 4 repeats. So here's the deal. If you think of this as the remainders by dividing by 4, it's going to go to these 4. So let's kind of write this out. I to the 0 is 1. I to the first is I squared's negative 1. I cubed is negative I. Think of these as the remainder after dividing by 4. So it doesn't take that much time, like write down I to the 0, I to the 1, I squared, I cubed. The first 3 are easy. It's the I cubed you might have to do I squared times I to figure it out. So if I want to find I to the 17, here's what I do. Take 17 divided by 4. It goes in there how many whole times? 4. And what's your remainder? 1. So this is going to be I. This is the exponent up here. This is the remainder. No remainder, remainder 1, remainder 2, remainder 3. So then, if I want I to the 200, thank you. What's 200 divided by 4? There's no remainder, right? So what would that be? 1. All right, let's do another one because I'm seeing some very confused looks. Let's do I to the 23rd power. You could even, like, if you can think of multiple, okay, let me maybe say it a different way. Okay, let me say it a different way since I've got so many confused looks. Let's try this another way. What is the highest multiple of 4 in here? 20, right? Yeah, you're right. Okay, you're right. Okay, 20. How much is left over? 3. Then you go to I cubed. Does that make a little more sense? Go up to a multiple of 4, and then however many is left over, that's the power of 3. So now that's going to be I cubed, which is my I squared times I, so it's negative I. All right, so those are called the powers of I. So now let's look at number 4. If I want to simplify, here's the big idea. I equals the square root of negative 1. So what you're always going to do now, whenever you have a negative under a square root, is we're going to pull the negative out. Okay, it has to come out first. So the square root of negative 1 is I. And what's the square root of 16? 4. All right, now we don't usually put I times 4. We're going to tidy that up and call it 4I. All right, letter B. If I have the square root of negative 27, the very first thing I do is I pull out the square root of negative 1. Now, I know some of you have very, very quick thinking. You can then begin, anytime you see a negative, pull I out. You can start, I'm going to do it for a while, but then I'll start skipping. We're going to start skipping this step and just put I, because that's what I is. It's the square root of negative 1. Now, the square root of 27 is the square root of 9 times the square root of 3. So that's 3I square root 3.
Could you write it 3 square root 3I?
That's a great question. We typically don't put I after a square root because it might look like it's under the square root. Now, if I have a fraction, like square root 3 over 2, I could put the I beside the fraction. That, as long as it's sitting beside the fraction, that's okay. All right, let's try letter C. This is going to be negative 1, square root negative 1 times square root 12. So that's I times, and I'm going to make that square root 4 times square root 3. So that's 2I square root 3. I'm going to pause a moment, and I want you to try letter D. Please, please do not do E, because something special happens on E. But let me pause and let you try letter D. Try and simplify that square root. All right, I'm going to start it. This is square root negative 1 times square root 108. That's I times, now this one took a little bit. It's going to be the square root of 36 times the square root of 3. If you didn't quite get it right away, say you started with a 4, then you'd have to keep going. And that's okay if you don't get the greatest perfect square factor out. You just keep going. All right, so now letter E. Here's where it can get a little tricky. This is 5 times square root negative 1 times square root 2. This is square root 1 times square root 8. So I need you to be hearing me. The product property for radicals does not work for negatives. Let me put this underneath here. Recall. The square root of a times square root b equals square root a times b only if a is positive and b is positive. So you may not have really paid attention to that teeny tiny part because I would get 2 different answers depending on which way I do it. And math is about rules that work all the time. So this is going to be 5i square root 2 times 4i times, now can you handle if I change square root 8 is 2 square root 2? Can you handle that? That's 4 times 2. So I'm going to get 4 times 2 is 20 times 2 would be 40. I times I is I squared. And then I have square root 2 times 20 times 4, right? No, 20 times 2. Yeah. Square root 2 times square root 2, isn't that 2? And then, what is I squared? -1. So this is -80. So do you see, if I had not pulled the i's out first, then I would have gotten a positive 16, and that would have been a positive 80. So let me say this again. That product property for radicals only works if the radicands, what's underneath the radical, are positive. So what you must do, if you have negatives under a square root, you have to pull the i's out first. The square root of -1s have to come out first. Otherwise, you're going to get a different answer. All right, letter F. This is 12 times the square root -1 times the square root 36. So I get 72i. So this is just simplifying with the square root of -1. So the big idea today is I equals, let's write this again, okay? I equals the square root of -1 and I squared equals -1. Okay, this is what's new today. So complex numbers are numbers that can be written in the form a plus bi, where a and b are real numbers. A is called the real part, bi is called the imaginary part. Standard form of a complex number is a plus bi. So let me talk about this diagram that's to the right. Everything now is considered a complex number because all of our real numbers just mean that the imaginary part is 0, and that's okay. So everything is a complex number. Underneath the complex numbers, we can split it into real numbers and imaginary parts, okay? Imaginary. Under the real numbers, you had rational and irrational. Rational numbers can be written as a ratio of 2 integers, okay? People say, when you say fraction, that's not square root 3 over 2. It has to be a ratio of two integers. Irrational are numbers like square roots, and pi. Under the rational are the integers, and under those are, we actually had one other one, whole numbers include 0, and then the natural numbers. So from this moment forward, everything is a complex number. We just have a real part and an imaginary part. All right, so number 5 says write in standard form. Can you see where I'm headed? Can anybody tell where we're headed? Where are we headed? Look at number 5. Quadratic formula, okay, and quadratic equations. Now we can handle getting a negative under the square root, okay? So watch what you're going to do for number 5. I'm going to split this. Always pull out a negative under the square root first. This will be 6. So you get 6 plus 4i. All right, I'm going to pause, and I want you to try number 6. Look at number 5 as a model. And if you remember, when we were solving quadratic equations using quadratic formulas, I said, hey, there's something that's going to happen that, let's be proactive and split. Here it is. It's the complex numbers. A plus bi form. This works naturally then. Are you getting 9 over 5 plus, and that's just an I, because 2 times 5 is 10. So we are always right in A plus BI form. Okay, write your final answers in A plus BI form. All right, to add and subtract complex numbers, you're going to treat I, because I is a square root, you're going to treat it like radicals. Remember, if I had 5 square root 2 plus 7 square root 2, it was 12 square root 2. So I is just a square root. So what you're going to do is this is going to be 2 plus negative 6 is negative 4. 3i plus 10i, plus 7i is 10i. Now, are you ready? Let's see if we can handle this. Can you see this is 5 plus 6i plus 2 plus 7i? Can you handle it now? Square root of negative 1 is I, so I'd like to start skipping this step. Anytime you see a square root with a negative, pull the square root negative 1 is I. If you need to keep doing it, keep doing it. So that's 7 plus 13i. In number 9, be careful. Anytime you are subtracting with a parenthesis, what do we have to remember to do? Distribute. Good job. So 4 minus 2i, that becomes plus 2 minus 7i. Students tend to like complex numbers because they're very simple to work with. All right, multiplying. You are going to multiply using FOIL like you did before, but then when you get to your final answer, we never leave I squared. What is I squared equal to? -1. So watch what we're going to do. I'm going to do the first one with you, then pause and let you work. 2 times 3 is 6. The outer is 10i. The inner is minus 12i minus 20i squared. So do you see the FOIL? The first, the outer, the inner, and the last. So this is 6 minus 2i, and then you're always going to replace I squared with -1. So it's 26 minus 2i. All right, try 11 through 14. I'm going to give you a few minutes. Head start. Do as many of them as you can. Number 11, check it. I got -16 lost 3i. Did you get that? Yep. Okay. Keep working. Where'd you get 28 from? Because isn't that -2? You're adding. You multiply next. All right, number 12, remember, when you have a binomial squared, 2 minus 4i, the quantity squared, you're going to make that 2 minus 4i times 2 minus 4i. I got -12 minus 16i. Okay, keep going, 13 and 14. Something weird happens on 13 and 14. If you've gotten that far, something weird should have happened. Let's see. Why did you change that to multiplication? You're adding these up, so you've made a, this step's right, but it's there, you made a mistake somewhere. All right, I got 49 minus 7i plus 7i minus I squared. So do you notice the outer and the inner canceled? And then I'm getting minus -1. I got 50. How many of you got 50? You got it? Awesome. All right, so something similar happens here. I get 25 minus 15i plus 15i minus 9i squared. You should get 34. Now, this is not an accident. Here's a big idea. If you take in general a plus bi times a minus bi, so this is going to give me a squared minus abi plus abi minus b squared I squared. So this is actually going to give you a squared plus b squared. Now we can factor over the complex numbers. For example, if you want to factor x squared plus 9, that's going to be x plus 3i, x minus 3i. Cool connection. We had not been able to do that previously. And it does not factor over the real numbers. All right, so back to 13 and 14. It was leading me somewhere. So in 13, if I have 7 plus I times 7 minus I, so if I'm taking the same a and bi but just changing the signs, that makes the imaginary part disappear, doesn't it? Do you see that? When I take 5 plus 3i times 5 minus 3i, there's no more I left in the problem. So that leads me to something called a complex conjugate. So if I have a plus bi, its conjugate is a minus bi. The purpose is to eliminate the I part. The purpose is to eliminate the I part. So this will lead me to our very last thing. When you divide complex numbers, you're not allowed to have an I in the denominator. So in number 15, where I have 2 minus 3i over 1 plus I, I'm not allowed to have the I in the denominator. So what I'm going to do is I'm going to multiply by the conjugate of the denominator. So if I have 1 plus I, I'm going to multiply by 1 minus I. And I'm going to multiply by 1 minus I over 1 minus I because that's technically 1. So watch what happens. I'm going to FOIL the numerator and I'm going to FOIL the denominator. So I get 2 minus 2i minus 3i plus 3i squared. So I'm FOILing in the numerator and I'm FOILing in the denominator. Down in the denominator, I'm going to FOIL and get 1 minus I plus I minus I squared. So that's 2 minus 5i plus 3 times negative 1 Down in the denominator, the outer and the inner cancel, which is what I wanted. Okay, I wanted to eliminate I. So then I get 2 minus 5i minus 3 over 2. Now, this is not a plus bi form. This is a plus bi divided by another number. So you're always going to be required to split them. I goes on the side of a fraction. Okay, I goes on the side of a fraction, and I goes in front of a radical if it's just a radical. Okay. All right, questions on what we did. So do you see I no longer have an I in the denominator? I moved it. All right, number 16. The conjugate is whatever you have in the bottom, the opposite sign. So if I have 3 minus I, its conjugate is 3 plus I. I don't change the sign of the 3. I'm just changing the sign in between, okay? All right, I'm going to pause now, let you FOIL the numerator, FOIL the denominator, and simplify it the whole way. Look at number 15 as your model or your guide. If your denominator doesn't cancel out the i's, you've made some sort of mistake. And try to go nice and slowly as you work these out because there's lots of little areas to make mistakes. So if you kind of show more work, I think that will benefit you. So I have 15 plus 5i plus 6i plus 2i squared over 9 plus 3i minus 3i minus I squared. So I get 15 plus 11i. Now, if you would get comfortable, what's I squared? So guess what? Anytime you see I squared, it's going to flip your sign. So I start doing that once I'm comfortable. Then I get 9 plus 1. That's 13 plus 11i over 10. And then we're going to split it because we've got to put it in a real part plus an imaginary part. So let me kind of go over this. A is the real part. BI is the imaginary part. So when you have one fraction, that's not a separate real part plus an imaginary part. All right, so what I want us to do is to do a reflection here. Write down on your own, how is addition and subtraction of complex numbers similar to addition and subtraction of algebraic expressions? How is multiplication of complex numbers different from FOILing an algebraic expression? What is the imaginary unit I? what's I squared? And then what are any remaining questions you might still have?